In this video, I'll show you how to use StatCrunch to compute a regression line for two quantitative variables. This video will have two parts. The first one is just the clicks, and then the second one I'll go back and talk about what this means. So first start with two variables in two columns, and we want to go to stat, regression, simple linear. So we have a regression line that we want to look like y equals mx plus b. So we choose simple linear. These other types of regression lines are not what we're learning in class. So we need to choose our x and our y variable. In some cases, the variables won't matter and you can pick x or y, either one. This one happens to be the case. Other times you need to be specific and make sure that your response variable is y. So I'm going to choose grocery store for x and then convenience store for y. And then we are not going to do a hypothesis test, but you can just keep that button clicked anyways. Go down the line. We want a fitted line plot, and that's all we want. We don't need to save anything. You can put an x-axis label if you want on your graph and a y-axis and a title. To get this quickly done, I'm just going to push compute. All right, so here we have our regression equation. It's the fourth line down, or rather the third after the bolded line. So the cost of sugar at a convenience store for 5 pounds is equal to 2.34 plus 1.03 times the cost of the price of the sugar at a grocery store. We had a sample size of 8, and here is our correlation coefficient, so you don't have to do that separately. And then here is r squared. Of course, turn that into a percentage. The rest of these outputs are important, but we're not going to talk about them right now. This has simply come up with the regression equation, and then on the next page, we have our fitted line plot. So here is the line that is graphed that best fits the data. So this is the equation. This is the line that we have the equation for in the previous page. And if you hover over the line, then you'll see the equation of the line. So now I'm going to go back and talk a little bit more about this output, but those were the clicks to get to this step. All right, so back on this output, the second line is going to give you the dependent variable. It just labels the variable. The independent variable is your x, so that is labeled for you. And then the regression line, it doesn't use y's and x's and hats. It actually puts in the names of the variables, so there's a little bit more meaning. There's also a lot of decimal places, so you might want to round those to fewer decimal places if you don't quite need that much precision. The sample size is there. The correlation, recall that goes from -1 up to +1. R squared, we have this sentence. It looks like about 22% of the variation in the response. So the price of a sugar at the convenience store is explained by the price of the sugar at the grocery store. So 22% is pretty low, so that means that there's a lot of other variables that we did not factor into this equation that are affecting the price of the sugar at the convenience store. So that might be, I don't know, we didn't collect data on where the convenience store is. We didn't collect data on the brand of the sugar. We didn't collect data on, what else? How large the convenience store is. Maybe they can buy more in bulk and so they get better pricing. All those things are going to affect the price of sugar. So we didn't collect data on them. That's about 78% of the variation in sugar price is based on all those things that we didn't study. Down here is a standard estimate of the standard deviation. This is the little SE, standard deviation of the residuals. In general, we want this number to be smaller because it means our estimate is better, but it kind of is what it is. If you need a smaller standard deviation, then you need to use different data points in your model. Down here in the parameter estimates, notice we have intercept and slope. Here's the 2.33, which we see up here. There's the intercept. And then slope is 1.03. right up here attached to the x variable. The standard error is referring to like a sampling distribution. Basically, we took a sample and it fits a sampling distribution just like we talked about in previous chapters, except for instead of computing a proportion or a mean for a sampling distribution, we're computing intercepts for our sampling distribution. So there will be a standard error of that sampling distribution. And then the intercept can also be a number, so the sampling distribution can have a mean. There is a t-stat and a p-value, which we will kind of learn a little bit with hypothesis testing, but basically it's testing the significance of these estimates against 0. So if these estimates are significantly different than 0, then that means there is like an official slope. It's definitely different than 0, not just, looks different. So these p-values are actually quite large. So basically, this is saying that our slope and intercept are not that far from 0. And that kind of makes sense. If you look at all the points, they seem to kind of line up more like a flat pattern, except for that outlier, where it does kind of make sense that maybe this data doesn't really have a relationship between the two prices of these two different stores. Which could make sense that if they're different stores, maybe they aren't related. But again, R squared is not very large, so we'd probably need to collect some more data to make that conclusion. Let's go back. Down here is something called an Anova Table, which we won't talk about in this class at all, but you can notice that p-value is the same as the p-value there. And that there's this relationship. If you take the square root of this 5.48 number, you're going to get an answer of 2.3. So there's some fun relationships there. All right, so now I've talked a lot about a regression line and how to make it in StatCrunch.